Imagine you're sitting in a radio telescope control room at 3 in the morning. The screens are flickering, the data is streaming in. And then something appears that makes every scientist in the room go completely silent. A signal, coming from deep space, repeating with clockwork precision. Every 18 minutes, like a cosmic heartbeat that nobody can explain. That actually happened. And what NASA and astronomers around the world found may be the single most mysterious discovery in the history of modern astronomy. Today, we're going deep into this story. We're going to talk about what the signal is, where it comes from, what could possibly be sending it, and why the scientific community is genuinely divided about what this means for our understanding of the universe. Because the truth is, nobody fully agrees on what this thing is. And that alone should tell you how strange this discovery really is. So, buckle up, because this is one of those stories where the more you learn, the more questions you have. Let's start at the beginning. In January 2022, a paper was published in the journal Nature that sent shockwaves through the astronomy community. Scientists working with the Murchison Wide Field Array, a massive radio telescope located in the remote outback of Western Australia, announced that they had detected something unprecedented. A powerful burst of radio energy coming from a fixed point in the sky, repeating every 18.18 minutes with almost perfect regularity. The signal was bright. Incredibly bright, sometimes one of the brightest radio sources in the entire sky when it was active, and then it would go dark. For about a minute it would blaze, and then silence for 17 minutes. Then blaze again, then silence again, over and over and over. The object was given the name Gleam X J162759 5 to 523,000, 504.3. Not exactly catchy, but that's astronomy for you. And the moment researchers started trying to explain it, they hit a wall. Here's the problem. We know about objects in space that send out repeating radio signals. They're called pulsars. Pulsars are neutron stars, the collapsed cores of massive stars that exploded as supernovas, and they spin incredibly fast, beaming radiation out like a cosmic lighthouse. Some pulsars spin hundreds of times per second. The fastest known pulsar rotates over 700 times per second. The slowest known pulsars, the ones we call millisecond pulsars or slow pulsars, they might repeat every few seconds, maybe every 10 seconds at the very slowest extreme. But 18 minutes? That's not just outside the known range. It's not even close to the known range. It's so far outside what we thought was physically possible that when researchers first saw the data, many of them assumed it must be some kind of equipment error, a glitch. Interference from a satellite or a passing aircraft. Something mundane. Except it wasn't. The team went back through archival data and found that the object had been active before in 2018, pulsing away while nobody was looking at that patch of sky closely enough to notice. And the pulses were consistent, predictable, real. This was no glitch. Something out there in the universe was genuinely broadcasting on this bizarre 18-minute schedule, and it had been doing so for years without anyone realizing it. So what is it? Let's talk about the leading theories, because this is where things get genuinely fascinating. The first and most popular scientific explanation is that this is what's called an ultra-long period magnetar. Now, magnetars are a type of neutron star, just like regular pulsars, but they have magnetic fields so intense that they're almost beyond comprehension. We're talking about magnetic fields 1,000 trillion times stronger than Earth's. The energy stored in a magnetar's magnetic field is so immense that it can actually crack the surface of the star, causing what astronomers call starquakes, and release enormous bursts of energy in the process. Magnetars are already considered some of the most extreme objects in the universe. We've detected them before. But here's the thing: known magnetars spin down relatively quickly. Their rotation slows. And the theory goes that once a magnetar is spinning slowly enough, it should no longer be able to produce the kind of radio emissions we're seeing. It crosses a theoretical boundary called the death line, a region of parameter space where radio emission simply shouldn't be possible anymore. Gleam X, J162759, 5 to 523,504.3, appears to be operating well beyond that death line. If it is a magnetar, it's a magnetar that somehow defies the standard model of how magnetars are supposed to behave. It's producing coherent, powerful radio pulses when every equation we have says it shouldn't be able to. Some scientists think the answer might lie in the magnetic field itself. Maybe ultra-strong magnetic fields can sustain emission mechanisms far longer than our current models predict. Maybe we're missing something fundamental about magnetar physics. The discovery of this object has forced researchers to seriously reconsider whether our theoretical death line is actually where we think it is. But there's another theory, and it's even more exotic. Some astronomers have proposed that this object could be a white dwarf pulsar. Now, white dwarfs are completely different from neutron stars. They're the remnants of medium-sized stars, stars like our sun, after they've burned through their fuel and shed their outer layers. White dwarfs are much larger than neutron stars, roughly the size of Earth, and they spin much more slowly. And theoretically, a white dwarf with the right magnetic field configuration could produce radio pulses as it rotates. The 18-minute period would fit much more naturally with a white dwarf. A white dwarf spinning with an 18-minute period isn't physically strange the way an 18-minute neutron star is. But here's the catch. White dwarf pulsars are exceedingly rare. We've only ever confirmed one of them, a system called AR Scorpii, and even that discovery was groundbreaking and controversial when it was made in 2016. Could Gleam X be a second white dwarf pulsar? It's possible. But the energy output seems too high, too concentrated, too coherent for most white dwarf models to explain comfortably. And then there's the third category of explanation, which researchers don't say out loud very often, but which the data genuinely doesn't rule out, and that's the possibility that this is something we've never encountered before. A genuinely new type of astronomical object that doesn't fit into any of our existing categories. Something that the universe has been producing all along, but that we've never had the instruments sensitive enough to detect until now. Think about that for a second. We've been observing the sky for thousands of years. We've built radio telescopes for almost a century. And there might be entire classes of objects out there that we simply couldn't see until our technology caught up. Gleam X might be the first example of something that's actually quite common. A type of cosmic radio source that's been broadcasting across the galaxy for billions of years while we had no idea it existed. That possibility is humbling, and it's scientifically electrifying. Now, one thing that absolutely needs to be addressed, because it comes up every single time a story like this breaks, is the question of whether this could be artificial. Whether this repeating signal could be evidence of some intelligence out there in the cosmos. I know you're thinking it. I was thinking it too. And the honest answer from scientists is almost certainly not, but we can't completely rule it out based on the signal alone. Here's the thing. The characteristics of this signal, the frequency at which it broadcasts, the way the pulses are polarized, the intensity of the emission, all of these properties are consistent with natural physical processes. The pulses aren't carrying any encoded information that we can detect. There are no mathematical patterns within the pulses themselves that would suggest intentional communication. The signal isn't a narrow laser-like beam aimed specifically at Earth. It appears to be broadcasting in all directions, which is incredibly inefficient if you're trying to send a message. What we're seeing looks far more like a rotating object emitting radiation as a byproduct of its physical properties, not a transmitter built to say hello. The SETI Institute, the Search for Extraterrestrial Intelligence, has examined this kind of data before, and their criteria for what would actually constitute a suspicious signal are quite specific. This one doesn't meet those criteria. But, and this is important, the reason scientists are so careful about saying definitely natural is that we don't fully understand what we're looking at. And intellectual honesty requires acknowledging that gap. We know it's probably a natural object. We don't know exactly what kind of natural object. And in that space of uncertainty, responsible science keeps all doors at least cracked open. What really makes this discovery significant from a scientific standpoint isn't just the object itself, it's what it implies about how much we might be missing. The Murchison Wide Field Array was running a systematic survey of the sky when it caught this signal. It wasn't looking for anything specific. It was doing what's called a blind survey, covering large patches of the sky at radio frequencies and recording everything. And in that data, buried in the noise, was this repeating 18-minute beacon that had been going on for years. Now, think about how many surveys we've done. Think about how many wavelengths we've searched. And consider that this thing was there all along, and we only caught it because we happened to be doing a sensitive enough survey at the right frequency at the right time. How many more objects like this are there? Objects that pulse on timescales too slow for traditional pulsar searches to find because most pulsar searches are optimized for periods of seconds or milliseconds, not minutes or hours? Scientists now believe there could be an entire population of ultra-long period objects scattered throughout the Milky Way that we've completely missed simply because we've been looking with the wrong tools, in the wrong way, on the wrong timescales. This prompted a wave of new searches. Teams around the world started going back through old radio telescope archives with fresh eyes and new algorithms specifically designed to find slow pulsing objects. And they found more. In 2023, a different team announced the discovery of another ultra-long period object, this one with a period of about 21 minutes, even slower than Gleam X. And then another was found, and another. Each one slightly different, each one adding a new data point to a mystery that's growing more complex the more we look. This is how science actually works in real life. Not with a single dramatic revelation, but with a cascade of discoveries that each open up more questions than they answer. Gleam X wasn't the end of the story. It was the beginning of a new chapter. Let's talk about where this object actually is, because the location matters. Gleam X is located approximately 4,000 light-years from Earth. That means the radio pulses we're detecting right now left their source 4,000 years ago. When this signal was first emitted, at least the signal we're currently receiving, the Great Pyramid of Giza, had just recently been completed. The Bronze Age was in full swing. Writing was still a relatively new technology for human civilization. And out there in the galaxy, this object was already broadcasting its 18-minute rhythm into the void. We're receiving ancient light, ancient radio waves, the echo of some exotic physical process that's been running uninterrupted since before most of recorded human history. And we're only now, in 2022, building the instruments sensitive enough to listen. There's something profound about that, something that really puts the scale of the universe in perspective. We think of space exploration as something we're doing, something active and aggressive and forward-moving, but so much of astronomy is actually archaeology. We're not observing the universe as it is. We're observing the universe as it was, across distances so vast that the light from distant events takes thousands or millions or billions of years to reach us. 4,000 light-years is actually relatively close in cosmic terms. Our galaxy alone is about 100,000 light-years across. Gleam X is practically in our backyard, a near neighbor by galactic standards, and it's still sending us signals from before the fall of Troy. Now, here's something that makes Gleam X even stranger. The signal disappeared. After the initial detection and the excitement of the 2022 paper, follow-up observations were conducted. Teams pointed their telescopes back at the same location, expecting to find it still pulsing away. And they found nothing. The object had gone quiet, completely silent, no signal at all. This happens with some natural radio sources. They can have active periods and quiescent periods. Magnetars especially are known to go through bursts of activity followed by long periods of silence. So this wasn't necessarily alarming, but it did add another layer of mystery. We caught it during an active phase. We don't know if it will become active again. We don't know how long the quiescent periods typically last. We don't know if the 18-minute period will still be exactly the same when and if it turns on again. And without more data from an active period, it becomes much harder to pin down exactly what physical mechanism is driving those pulses. This is the frustrating and thrilling reality of observational astronomy. You can't control your subjects. You can't ask a distant cosmic object to hold still and emit conveniently for your study schedule. You point your instruments at the sky, you record what you find, and sometimes the universe shows you something extraordinary for a brief window and then closes the curtain before you've had time to fully understand what you were seeing. The broader context here also touches on one of the biggest open questions in astrophysics right now, the nature of fast radio bursts, or FRBs. Fast radio bursts are incredibly brief, incredibly powerful radio flashes from distant galaxies. They last milliseconds. Some of them repeat, most don't. They were first discovered in 2007, and for years after that discovery, scientists argued fiercely about whether they were real or some kind of instrumental artifact. They were real. And now we've detected hundreds of them from galaxies billions of light years away, and we still don't have a definitive, unified explanation for all of them. Some FRBs appear to come from magnetars. In 2020, scientists detected a fast radio burst from within our own galaxy from a known magnetar called SGR 1935 plus 2154, which was the first time we'd ever caught a magnetar producing an FRB-like signal. That was a landmark discovery. It strongly supported the idea that at least some FRBs are magnetar-produced. Gleam X and objects like it might be related to this picture in a complicated way. If ultra-long period magnetars exist and can produce bright radio emission on minute-long timescales, maybe the physics that produces those slow pulses is connected somehow to the physics that produces the millisecond scale FRBs. Maybe these are different manifestations of the same underlying processes, different regimes of the same extreme physics that governs the most energetic magnetic objects in the universe. We don't know. That's the honest answer. We don't know. And that answer, frustrating as it might feel, is actually the most exciting thing that can happen in science. Because not knowing means there's still something left to discover. It means the next paper, the next observation, the next clever algorithm applied to old data might be the thing that cracks this open. Think about what it would mean if we figure this out. Not just for astronomy, but for physics. If Gleam X is a magnetar operating beyond its theoretical death line, that tells us our understanding of neutron star physics needs revision. That revision could have cascading effects on how we model everything from gravitational waves to the equations of state for matter under extreme density, matter so dense that a teaspoon of it would weigh 1 billion tons. These are fundamental questions about the nature of matter itself. If it's a white dwarf pulsar, that tells us white dwarfs are more dynamic, more capable of exotic behavior than we thought. And white dwarfs are enormously common. They're what most stars in the universe eventually become. Rethinking what white dwarfs can do means rethinking a huge fraction of the stellar population of the cosmos. And if it's something genuinely new, if Gleam X represents a class of object we've never categorized before, then we're looking at a complete expansion of our cosmic taxonomy. A new branch added to the tree of known astrophysical phenomena. A new chapter in the textbooks. Whatever the answer turns out to be, it matters. This isn't idle curiosity. Understanding the objects in our universe, understanding the physical processes that produce signals like this, is part of how we understand the universe itself, and by extension, how we understand our own existence within it. We are made of elements forged in stellar interiors. The iron in your blood was synthesized inside a massive star that exploded as a supernova before our solar system formed. The calcium in your bones, the oxygen in your lungs, all of it was produced by nuclear reactions in stars, scattered by stellar deaths, and gathered up again by gravity to form new stars, new planets, new life. We are, in a very real and non-metaphorical sense, the universe looking at itself and trying to understand what it is. When we point a radio telescope at the sky and find something that doesn't fit our models, and we argue about what it could be, and we go back to the data and build new theories and design new instruments to test those theories. That's the universe trying to understand its own extreme physics through us, through our curiosity and our instruments and our willingness to sit with a mystery and say, I don't know yet, but I'm going to find out. Gleam X is sitting out there in the constellation Circinus, about 4,000 light years away, silent for now. Whether it switches back on next year or in a century, or whether that brief window we observed will turn out to be all we ever see of it, we don't know. But what we've already learned from it has permanently changed the landscape of radio astronomy. It opened our eyes to a new way of searching for objects we'd never thought to look for. It gave us a new category to pursue. It reminded us, once again, that the universe is stranger and richer and more surprising than even our best theories can fully capture. And honestly, that's why I love this stuff. That's why stories like this one matter. Not just because of the cool factor though, let's be honest. An 18-minute repeating signal from 4,000 light years away is incredibly cool, but because of what it represents. It represents the edge of our knowledge, the frontier, the place where what we know ends and what we're still figuring out begins. That frontier is always moving forward, and every time a discovery like Gleam X pushes it a little further out, we understand our universe a little better. We understand ourselves a little better. So the next time you look up at the night sky, and I genuinely hope you do look up sometimes, away from the screens and the noise, remember that every point of light you see is broadcasting. In visible light, in infrared, in radio waves, in X-rays, and gamma rays, the universe is full of signals. Most of them we can't detect yet. Some of them, with the right instruments pointed in the right direction at the right moment, turn out to be something no one has ever seen before. Gleam X is one of those signals, and somewhere out there, there are hundreds more like it, waiting for us to build the instruments sensitive enough to hear them. If this video sparked something in you, that feeling of wonder, that pull toward the unknown, hit the like button and subscribe so you don't miss the next time we go deep into one of these mysteries. And I want to know what you think in the comments. Do you think Gleam X is a magnetar, a white dwarf pulsar, something else entirely? Drop your theory down below. Some of the best conversations I've ever had have started in the comments on videos exactly like this one. So let's talk. I'll see you in the next one.